Hi everyone, welcome back to our seminar. Today Gabor Lippner is going to tell us about pretty good fractional revival via magnetic fields with theory and examples. Yeah.
Okay, thank you very much for coming, and thank you very much for inviting me to give this talk. So this is going to be an uphill battle against technology. I apologize ahead of time for any mishaps that may happen. This is joint work with my former student Whitney and Mark. And so basically, we have two papers, one that has been out for a while with like almost uncountably many co-authors. And I'm not going to really talk about that now, but we still build in many ways on that work. And then we have our recent preprint. That's just the three of us. It's on archive. And I mean, this project has been an ongoing effort for almost 5 years now. And I'm really ashamed that it only got to this point by now. And I already gave some talks about it earlier, I think in 2022 at the CMS meeting and maybe at some other venues as well. But I feel like now it has sort of matured enough that that we understand what we want to say, and we kind of say it in a probably a polished enough way that I would hope that it's final. And though the main ideas have been around for basically 5 years, COVID and then the delay with this other paper sort of got us delayed quite a bit, and that's why it's only finished now. But okay, so life happens. All right, so what am I going to talk about? We are studying the quantum walk as is customary. So we fix a finite graph, but really, and then associated Hamiltonian matrix, which we're going to take just the adjacency matrix of the graph and then add some diagonal matrix to it, which describes this magnetic field in the physical setting. But throughout the way we wrote the paper, there's really no graph. It's just a symmetric matrix with some diagonal entries added for control. Of course, we like to think of the matrix as coming from a graph to make it more sort of graph theoretic, but essentially the whole thing can be done for arbitrary real symmetric matrices. And then the quantum walk itself is this evolution of e to the it, so t is some time variable times this Hamiltonian matrix. So ut is a symmetric unitary matrix. How this comes up from from a physical system, it's described many times now in the literature, so I just briefly will allude to it. Kind of the idea is we have the graph describing a network of spin particles, electrons, for example. And the nodes are these particles. The edges describe local interactions between the particles. And so this is modeled if we have n particles by a 2 to the n dimensional, 2 to the n complex dimensional system. And there is a Schrodinger's equation behind this whole thing that sort of describes the time evolution. But for the sake of most of the theory that is done in the algebraic graph theory context, we focus on what is called the one excitation subspace of this huge 2 to the n dimensional space. Essentially, it's the subspace or the kind of the how to say. So it's the subspace of this big space where at any given time only one of the n particles is not in the ground energy state. So this is sort of an n-choose one dimensional subspace. Okay, let's see if I can write on this slide. So it's an n choose 1. So it's an n-dimensional subspace in this 2 to the n-dimensional big space. And it turns out that this is invariant under Schrödinger's equation. So whatever happens in this subspace remains in this subspace. And after some calculations, it turns out that in this subspace, the evolution is given by the quantum walk. So that's sort of the physical motivation or the physical background. Again, it has been described in literature countless times now. And so, which is what allows us to focus on this simple, well, it's still not simple, but sort of this more graph theoretic notion of quantum walk. Okay, so what is usually studied in this quantum walk, or maybe the most studied, there are other things too, is what is called state transfer. So you have your graph, you have two nodes, U and V, and so you start your system with U being the only excited node, and then you let it evolve, and you're looking for a time at which V is the only excited node. So I said only one node is excited, but that's actually a linear combination of which node is excited. So we want kind of a pure state where U is the only excited node with the full weight. And then we want to, at the time t, we want to read it out at a moment where V is the only excited state, and it's not a linear combination of other excited states. And so we're looking for a time t at which the UV entry of this evolution matrix is absolute value 1, which is exactly this. And sort of the physical motivation for this state transfer, again, is it started out as a tool to move quantum information from point A to point B, or in this case, point U to point V, where this is really a physical object, this graph. It's realized as a physical network, and I'm sitting at one end of this network, you're sitting at the other end of the network, and I want to send you my favorite qubit. So I sort of encode the qubit on the system, then wait until the appropriate time, and then you read it out at your end, and it should be the same qubit, more or less, if you're reading it out at the right time. And indeed, there is this state transfer. And okay, so the question was how to design graphs that have this state transfer property, and it turns out to be quite a challenge. So what is fractional revival compared to state transfer? Fractional revival is a similar, though slightly more permissible thing. Basically, what we want is that at a given time, if I look at this UT matrix, and I look at the 2x2 submatrix given by my two nodes, I want it to be a unitary matrix itself. So UT is already unitary. That's not going to work like that. Sorry. So UT was already unitary. And then suppose that UV is kind of the top left 2x2 corner. So we want this corner to be unitary itself. But that implies that these will be 0 because the row norms are 1. And then this is something that we don't really care about. So basically, fractional revival on two nodes asks for a time where this UT matrix has this block diagonal structure. Once it's block diagonal, the blocks must be unitary themselves. So that's not an extra condition. What matters is the block diagonal structure. And so state transfer would be a special case of this. If A and A prime are 0, then that corner matrix would just be this 0, 1, 1, 0 matrix, or some complex variant of that. And so this would get us back to the usual state transfer question. So what fractional revival does, it doesn't ask the state from U to be transferred to V perfectly, but it wants the state to be fully supported on the union of U and V. And so you may wonder what this might be good for in the physical setting. And one of the motivations that why people started looking at this is because this could be a protocol for generating so-called entangled states. So I don't want my information to be sent to you, but I want that in the end, we end up with qubits that are sort of dependent on each other. So this is called fractional revival, and this has been studied for a while still, and it's still hard to design graphs that have this property. Now, when we started thinking about this, we started thinking about it on two nodes, but then quickly realized that we can actually generalize this to a subset of nodes. So state transfer doesn't really make sense for bigger than two vertex subsets, but fractional revival does. Because once you realize that you're only asking for this block diagonal structure, well, there's no reason to insist on one of the blocks being a 2x2 block. You could fix your favorite subset of nodes and then ask for the matrix to have this kind of block diagonal structure, where now this S, this Z is this S by S submatrix. And so we want to say that the graph, or this subset S, has fractional revival in the graph if at some time t, we have this block diagonal structure where one of the blocks corresponds to this S by S submatrix. Now, this is all good, but there is a caveat. Oh, the caveat is on the next slide, I think. So this is a generalization of the 2x2 case, and can be used to generate entanglement among more than two particles. Okay, so I'll come back to the caveat in a slide or two. Okay, so before going there, I now want to start talking about the pretty good version of fractional revival. So as I mentioned, finding examples of fractional revival is difficult. There are few graphs that have it, and it's hard to verify and hard. It's a hard question. So this is already the case for state transfer. And so what people started doing is relaxing the condition of having a single time where state transfer happens, and instead asking for, okay, what if I don't want 100% transfer fidelity? I just want to make sure that if I wait a certain amount of time, I can get it as close to being a full state transfer as I want. So the first such concept was pretty good state transfer, where I didn't want U of t at UV to be 1, but sort of something like approximately 1. And to make this precise, I want a sequence of times at which this UV entry of the U matrix kind of converges to 1 as this along this sequence of times. So now we have to, or we want to formulate this for this PGFR, the pretty good fractional revival. And again, so what was fractional revival? It was that we have this block diagonal structure. So then pretty good fractional revival is going to be, okay, there's not a single time where we have the perfect block diagonal structure, but we want to have sort of a sequence of times along which the matrix sort of converges to a block diagonal matrix. So how to formulate that? at any time, we can look at this S by S submatrix of UT, this corner, this S by S corner. And so we want a sequence of times when this becomes unitary, or this converges to a unitary matrix. So in a topological language, what we're doing is we're looking at the closure of all the possible submatrices we get. So we take this, this submatrix for all time. This is some subset of all S by S matrices. We look at its closure, and we want to find a unitary matrix in this closure. So now comes the caveat. The problem with this definition is that it's always going to be true. No matter what your graph is, there's always going to be a unitary matrix in the closure of this set, namely the identity matrix, because we know that every graph is almost or asymptotically periodic. So it's not just that there will be a block with the identity, but the whole matrix will be approximately the identity. Like there is a sequence of times such that U of ti minus the identity goes to 0. And of course, for this sequence of times, if I look at the block, it is going to go to 0 as well. Or it is going to converge to the identity matrix as well. And the identity is unitary. So this is not an interesting question. So to get rid of this uninteresting case, we need to insist that this unitary block that we find has at least 2 distinct eigenvalues, which means that it's not the identity matrix, basically, or not a scalar multiple of the identity matrix. Okay, so let me summarize what our notion of pretty good fractional revival is. So we fix a set of nodes in the graph. We say that this set of nodes has pretty good fractional revival. If I look at the S by S submatrix of my UT, so right, this is UT here. For all say non-negative time, I intersect it with the unitary group on this S by S sub matrix, so the unitary matrices on S. And I want to find one element of the intersection that's not just a scalar multiple of the identity matrix. Okay, this is how we define pretty good fractional revival. So you may think that there's still a problem here. Okay, what's the problem? What could be the problem? The problem could be, okay, so I really want some entanglement. So I really don't want this corner matrix, even if it's unitary. I don't want it to just be a diagonal matrix. Even if it's not the identity, but it's if it's some diagonal matrix, that still means that at that moment, there's no entanglement between my nodes. It's just they're all kind of individually coming, like all the weight on that node is coming back to itself instead of kind of spreading out on the subset. So you may think that this is still not the right definition, but it turns out that this cannot happen as long as the graph is connected. And this is an observation that's due to Ada Chan. And this was essentially contained in the first of the 2 papers. But in this context, we make it more explicit in this paper. Basically, once you know that there is a unitary non-identity or non-scalar multiple of the identity matrix in this subspace, or in this corner, it automatically follows that there will be a non-diagonal matrix. So basically what happens is this guarantees that there will be also a non-diagonal matrix in this closure. I won't have time to explain this. This is really kind of subtle, but it's very reassuring that it's enough to exclude multiples of the identity, and then that automatically excludes having only diagonal unitary blocks in the closure. You will always find sort of a non-trivial block, which is a unitary block matrix that's not just a diagonal matrix. So it turns out that you don't need to worry further about sort of having only trivial examples. Okay, so this is the end of the introduction. I want to see if there are any questions. This is where being online is not helping, but okay. I'll take a moment to breathe and see if there are any questions so far. Okay, I'll take there are no questions. You can always email me questions, of course, or just wait until after the talk. Okay, so what the talk is really going to be about is how to find examples of pretty good fractional revival if we are allowed to add these diagonal terms to the matrix. But in order to get there, so the goals are the examples. But to get there, we develop some theory of, first of all, how to characterize pretty good fractional revival, and then we'll see some conditions that are equivalent, that are more like spectral conditions. And then we will develop some methods on how to verify that those conditions hold. And then that'll give us sort of a blueprint on how to construct examples. But I'll start first by deriving some like sufficient and necessary conditions for pretty good fractional revival. And this will be a generalization of this Kronecker condition that is sort of well known in the pretty good subfield of state transfer. Okay, so I'll try to scribble here. So imagine that someone told us that at this time t, the UT matrix has this block structure, where Z is going to be my unitary block matrix, and then I don't know what's here. So this is U of t. And this is the same whether you want exact fractional revival or pretty good fractional revival. It's easier to explain for exact, but for pretty good, you can always just take the limit on this sequence of times. So whether this is exactly equal to UT or approximately equal to UT doesn't matter for this for the sake of this explanation. But since UT can be written in a spectral decomposition form, to write smaller. So if we have eigenvectors phi1 through phi(n) and eigenvalues lambda1 through lambda n, then we know that we can express U of t this way. And what this implies, if we have at this time this block diagonal structure, that any eigenvector of H, if we restrict it to the subset S, it must become an eigenvector of Z. And not just that, But if I now look at the eigenvalue corresponding to that eigenvector, which is this number, it has to correspond, it has to be equal to the corresponding eigenvalue of my Z matrix. So if phi j restricted to S is some psi eigenvector of Z, then e to the it lambda j must be equal to the corresponding eigenvalue of Z. Now, what does this tell us? Suppose we have two different eigenvectors of H that restrict to the same eigenvector of Z. Then e to the it lambda of one of the eigenvectors is equal to the same eigenvalue as e to the it other lambda. So the two eigenvalues must then sort of be equal or approximately equal to the same eigenvalue of Z. So we get groups of eigenvectors of H where we know that the eigenvalues, the lambdas, must sort of behave the same way at this time or at this sequence of times. It must approximate the same given eigenvalue of Z. And so this gives rise to a partition of the spectrum. So the partition comes from, again, it basically comes from looking at when different, like you look at all the eigenvectors of H, you restrict it to the subset. And if you find two eigenvalues that have eigenvectors with the same restriction, then those two eigenvalues must be in the same group. And this is a binary relation on the eigenvalues. So again, two eigenvalues are related if they have corresponding eigenvectors whose restrictions are equal or scalar multiples of each other. And this binary relation extends to an equivalence relation. I mean, you just extend it. And the equivalence classes will be these parts. So pi 0 in particular will be all the eigenvalues where the eigenvector restricts to just 0. That's sort of always sort of it happens, but those eigenvalues will not really play a role. But for those eigenvalues where the eigenvector restricts to some non-zero thing, they'll be naturally grouped into some number of groups. And in each group, all the eigenvalues at this time t, sort of the e to the it lambda, must approach the same unit complex number. Now, it turns out that this partition, so we're not given the Z matrix. That's one of the problems, right? We just want some matrix. But it turns out that the partition is encoded in the graph or in the H matrix itself, and is not really dependent on the Z matrix. And it can be described by this formula here. So basically, the EI is just the spectral projection to the ith eigenspace of the H matrix. So H can be written as the sum of lambda I EI, where these are the spectral projections. And then it turns out that two eigenvalues are going to be related to each other if and only if this product is non-zero, where ds is the matrix which is diagonal. It has ones on the corner and then 0 everywhere else. So this relation is not dependent on the Z matrix. It just depends on the graph and the subset. And then if you close this into an equivalence relation, it turns out that this gives this exact partition for that tells us which groups of eigenvalues must behave the same way at time t. Just to to give a parallel to the two-vertex case and the state transfer case, there we usually have only 3 parts. So we have a pi 0, and then a pi 1 and pi 2, or a pi plus and a pi minus. The most classical case is the state transfer, where it's a pi plus and a pi minus. The pi plus has the eigenvalues for which the eigenvectors restrict to a 1, 1, and the pi minus has the eigenvectors which restrict to a 1, minus 1. But since we're not talking about 2 nodes, we have an arbitrary subset, then we will have more of these parts. And the rule is that the eigenvalues in each part must sort of behave the same way. Okay, so I want to get to characterizing pretty good fractional revival. So far, we only identified that there is this partition that is encoded in the system, and that at this time t, or a sequence of times, these e to the it lambdas must converge to some unit complex numbers in each group. But it's now comes the part that we have to exclude the identity matrix again. So for each part we have we have one of these parts, and then we take an eigenvalue in that part of the spectrum, and then we look at e to the it lambda at that sequence of times that gives pretty good fractional revival. And we want this to converge to some rho j unit complex number that will be the corresponding eigenvalue of the Z matrix. So this will be, there's no Z matrix yet. We're kind of getting the Z matrix out of this, but this will be the eigenvalue of Z. And so the condition that Z is not the identity matrix means that we can't have these rows be all the same unit complex numbers for all the groups. So we have to be able to pick, for each group, we have to be able to pick one of these unit complex numbers and then find a sequence of times at which e to the it lambda converges to this picked number, this given number. It's not given, it's chosen, to this chosen number. But again, the point is that we cannot choose all of these rows to be equal. And so this depends on the partition, right? So the partition is given, and now we know which groups of eigenvalues must approximate the same unit complex number at these times. And we also want that these are not the same unit complex numbers. So this is a property of the partition, or like these groups of eigenvalues. We call this a non-degenerate partition. If you can actually choose these unit complex numbers, they're not all the same, and you can choose a sequence of times at which the eigenvalue, the lambdas in each of the group converge, e to the it lambda converges to this chosen complex number. And then the result is going to be that I take the graph, I look at this partition, which is given by that relationship that's here. So I look at the partition generated by this relation. And then I want to decide whether it's a non-degenerate partition or not. If it's non-degenerate, then this graph will have pretty good fractional revival. If it's degenerate, then it's not going to have pretty good. Well, if it's not non-degenerate, then it's not going to have pretty good fractional revival. And so this now becomes sort of, again, a number theoretic issue. And this is where the Kronecker condition comes in. And so what we did in this paper is we found sort of the correct generalization of the usual Kronecker condition to the case of more than 2 parts. So we are basically able to, if and only if, characterize when a partition is non-degenerate. And so it's this Kronecker condition. So let me try to compare it with the usual 2-vertex Kronecker condition. So the usual Kronecker condition says something like this. You have two groups, a pi plus and a pi minus. And so you want to choose integers for each eigenvalues. So the eigenvalues are lambda 1 through lambda n. And you want to choose integers L1 through Ln. And you want that the sum of the Li lambda i's is 0. And you want that the sum of Li's is 0. And then what you don't want is that the sum of the Li's in the plus group is non-zero. So for the state transfer, you don't want this to be 2. For pretty good fractional revival on two vertices, you don't want this to be 1. And this is the usual Kronecker condition. So how this changes when we have more than two parts. So we still want to choose an integer for each eigenvalue, and we still want this sum to be 0. But instead of asking the sum of all the integers be 0, we have to ask more. We have to ask that the sum of the integers in each part is 0, except for two parts, and it can be any two of the parts. I cannot prescribe which parts will not have a 0 sum. I just need to find two parts, and outside of those two parts, we want to be 0. But in those two parts, we don't want it to be plus and minus 1. Right? This is a generalization of the two-part condition. It's just written in a weird way, because if in the two-part condition, the sum is 0, and then the sum in one part is 1, then the other part is -1. So, but since we have more than two parts, we need to also say something about the other parts. So this was sort of a convenient way of writing this condition. So we get that the partition is non-degenerate if we can pick two of the parts such that all of these conditions cannot be satisfied at the same time. Or in other words, if the first two conditions are satisfied, then the third is not satisfied. This is a little complicated and slightly technical, but I still want to, let me see how I'm doing. I'm not sure how much time I'll have. I'll show you one direction of the proof, which is pretty standard, and maybe give an idea of the other direction.
There are roughly 12 more minutes.
12, okay.
Mm-hmm. Oh, well, less than that, yeah. Mm-hmm.
All right, so then I'm not going to give the proof for sure. So this is only a 55 minutes-ish seminar, or like that? Okay, sorry. So I'm gonna, okay, so we have this Kronecker condition. It is similar to the original two-vertex or two-part Kronecker condition. It's slightly different or slightly more involved, but it kind of has the same flavor. And then comes the real question. Okay, I get a graph. Say I can find these parts. But how can I verify the Kronecker condition? Sort of verifying the Kronecker condition is the weak point of this whole theory. And I only know one way of doing that, other than like explicitly computing the eigenvalues, which can only be done in very few cases. But if I don't have an explicit computation of the eigenvalues, the only method I still know is this field trace argument that Mark and I came up with some years ago. Basically, what we want for that is we want to find polynomials whose roots are exactly the numbers in these parts. So I want one polynomial for each part that gives the eigenvalues, whose roots give the eigenvalues in that part. And I need these polynomials to be irreducible over some relatively small field. And then I need two of the polynomials to have non-equal trace over degree. once I have that, so once I'm able to find such polynomials, and I'm able to show that they're irreducible, and then I can compute two of these trace over degrees, and they're different, then I win. And I basically can conclude that this graph has a pretty good fractional revival for that subset which generated my partition. So now the goal is, what I want to describe next is how I find these polynomials. And if you think back on the two-vertex case, or the state transfer case, these polynomials come from the characteristic polynomial of the graph. So usually what happens is the characteristic polynomial will factorize into 2 or 3 factors. One factor will be containing all the eigenvalues which restrict to 0. That's not interesting. And then there'll be a p plus and a p minus polynomial that sort of contains all the eigenvalues that restrict to, say, the 1, 1 eigenvector, and then the p minus is going to contain all the eigenvalues that restrict to the 1 minus 1 eigenvector, say, of the 0, 1, 1, 0 matrix. And so we wanted to generalize this this setup, and this led us to basically generalize the notion of cospectrality to a fractional setting. So now I'm going to fix a Z matrix, and I'm going to say that my subset is Z cospectral if I have an orthonormal basis of eigenvectors, so that if I restrict each of them to my subset, I always get eigenvectors of this Z. And if you do this for the 0, 1, 1, 0 matrix, you just get back the usual cospectrality notion. So this is a direct generalization of cospectrality. I can either change the 2 by 2 matrix to which I'm looking at, or I can look at a bigger subset and choose any matrix there and ask for all the I ask for an eigenbasis that restricts to eigenvectors of my matrix. And this is not the strong version of the cospectrality. This is the usual, this is the original version of of cospectrality. Strongness would assume something extra. It would assume that there's not just a orthonormal basis, but for any eigenvector of H. So that's a subtle point. It only happens when H has multiple H has eigenvalue multiplicity, in which case there is a difference of a orthonormal basis or all eigenvectors. And so here we only need a orthonormal basis that restricts nicely. And the really good thing about cospectrality in the original setting is it has many, many equivalent forms, and it can be sort of combinatorially verified by counting walks in the graph. And the nice thing is that in the fractional generalization, we have all the same characterizations. So what's written here, so I want to emphasize this one and this one as equivalent characterizations. So the second one, I take the kth power of my Hamiltonian matrix, and then the tilde just means restricting it to the S by S corner. And what this gives me, this condition tells me that we have cospectrality if for every power this restricted H to the K matrix commutes with my Z. And since H to the K in a graph is given by walk counts, this commutation relationship can be translated into a bunch of equations about walk counts. And in the 2 by 2 case, it's just going to be the usual equation that the number of walks from U to U equals to V to V. That's for the state transfer case. And then for the fractional cospectral case, it's like something that the difference between the k-length walks from U to U and the k-length walks from V to V are related to the number of k-lengths walked from U to V for every k in the same way. But you can generalize this walk count characterization to higher size subsets. And then the other nice equivalent characterization, which will be important for the polynomials that I want to describe, is you can take an eigenvector of Z extended by all zeros, and then sort of look at this walk module. So look at the linear space generated by applying the Hamiltonian any number of times to my vector, starting vector. And these are subspaces of Rn. And what I need is that these subspaces are pairwise orthogonal for different eigenvectors of Z. So this is, again, an equivalent characterization of this generalized Z cospectrality. So there are a few important things that are helpful for applications. First of all, that this Z matrix does not have to be a symmetric matrix, because we're not going to, this Z matrix may not be the actual restriction of the UT. Oh, I only need it to commute with the restrictions. And I needed to have eigenvectors. So it's actually enough to consider normal matrices instead of symmetric, which will be a real help when we're looking at examples of more than 2 nodes. And then if I can find a Z matrix that has cospectrality, this fractional, this Z cospectrality, and it happens to have only simple eigenvalues, then the whole thing becomes really nice. So the goal is always for us to find a Z matrix that has, so the subset, we want to find a Z matrix that has Z cospectrality, and this Z matrix has only simple eigenvalues. Because then every eigenvector in this previous slide, you have this subspace, and it turns out that the corresponding polynomial, so wait, I'm not starting to talk too fast. So each of these subspaces in turn is going to correspond to one of the parts in the partition of the eigenvalues. Basically, those eigenvalues will be the ones that restrict to this eigenvector of Z. And we can compute polynomials. Basically, the relative minimal polynomials of each of these vectors are going to give me the P1 through PS polynomials that capture the eigenvalues in that part. So this only works if Z has only simple eigenvalues. In the more general cases, it really becomes very, very complicated. So we don't really know how to use Z cospectrality if Z does not have simple eigenvalues. But once it does, then these relative minimal polynomials give me these P polynomials that capture my partition. And then this is where the magnetic field comes in. If I add the transcendental potential to the diagonal of this subset, then it turns these polynomials into irreducible ones. That's the standard argument that people have been using before. And so now all we have to verify is the trace and degree condition. Yeah, I have like not too many minutes left, right? Okay, so let me just summarize what's happening. So we want to construct examples with pretty good fractional revival. What's the blueprint? So I get the graph, I compute, I need to find a Z matrix for which my subset is Z cospectral. So that's the key step. And I need this Z matrix to be to have only simple eigenvalues. Once I have that, then I can get the eigenvectors of Z. And then for each of the eigenvectors of Z, I get a relative minimal polynomial of that vector according to my Hamiltonian. And this will give me a factorization of the characteristic polynomial of the Hamiltonian, and each factor will contain exactly the eigenvalues in each of the parts of my critical partition. Now, once I add the magnetic fields to the diagonal, these polynomials become irreducible. And so if I can verify this trace over degree conditions for 2 of the polynomials, then I'm done. It implies through this whole theory that I get pretty good fractional revival. And so let me just give you 2 types of examples that we found where this theory can be actually implemented. So first of all, in the 2-vertex case, we have found a bunch of families where we can explicitly find these polynomials. Well, there'll only be 2 of them. Because we can actually do all the walk counts, we can find the Z matrix explicitly, we can find the eigenvectors of the Z matrix explicitly, and then using the relative minimal polynomial machinery, we can actually compute every parameter that's involved here. In particular, we can compute the trace and the degrees of these polynomials, and you just find examples where they're different. So that gives you a pretty good fractional revival. And we have a bunch of these types of examples. They were all found by computer search, but it would be nice to sort of understand what makes them work, which I don't really do. It's kind of magic, but we already know that sort of cospectrality is kind of magic. So this is not so surprising that fractional cospectrality is also kind of magic. And then we have some examples with mod P symmetry. So that's kind of the only example we have where the subset is not two nodes. We need graphs that have some kind of prime order some kind of prime order automorphism. And then the Z, this is where it's important that my Z matrix is not normal, because for such automorphisms, this Z matrix works always. This is just the permutation matrix, which is not symmetric, but it's normal and only has simple eigenvalues. And this will commute automatically if you have an automorphism. It'll commute with any power of the adjacency matrix. So everything kind of works automatically. For this case, the only non-trivial step is finding examples where you can verify the trace over degree condition. And there are some tricks that we can use to build really a large family of examples where this works. And typically the idea is that this Z matrix has one special eigenvector, the constant vector, and then all the other eigenvectors are kind of these trigonometric ones. And so what we can show in many cases is that, in fact, the degree of the polynomial that is the relative minimal polynomial of the constant vector is going to be bigger than the degree of the other polynomials, or at least one of the other polynomials. And the traces are automatically different. So that happens to be enough to show that the degrees are different, because the trace has this transcendental component. Okay, so I'll finish by asking my favorite question. The whole theory relies on finding these relative minimal polynomials of given vectors, and then finding the trace and degree of these polynomials. And we don't have a good way of doing that. The only way is like either some explicit calculations on some very special graphs. And so I really want to see if there is, and if there is, what would be like a useful combinatorial theory for understanding these relative minimal polynomials. And then sort of corresponding to that, can we find examples with more than two nodes where there's it doesn't come from an automorphism. Right. Thanks for your attention.
Okay, thank you very much. There are some questions in the chat.
Okay.
So Hermie is asking how many parts of the support there should be, and that was around 12.
Right. I see. So we don't, like, as long as there are, so there's the pi 0 part, which sort of contains the eigenvalues that where eigenvectors restrict to 0. That is always sort of special. But other than that, if we have at least two parts and the non-degeneracy condition holds, that's enough. So even for a higher size subset, it is possible that you will not have more than two parts. It's a little hard to explain why or when that happens, but we have a good understanding of those, like how to find those parts once we know the polynomials, and we just need two of them, and we need the corresponding polynomials to be to have different trace over degree. And the directed network is a very, very, very good question. At first, I would be inclined to say that there must be something that won't work, because I know about some results of on directed graphs due to Ada and Tino and others, which have behavior that contradicts what I was saying here. So that indicates that directed graphs, there's something should be different. Yet I do believe that this Z cospectrality notion should be generalizable to sort of at least a Hermitian case instead of real symmetric. And this would be very interesting to look at and see how much of this can be preserved for that case. So that's, yes, and that would include like things like directed graphs.
Ada, has something to say?
I have questions. Hi, I like your background. Right? It's very
Thank
nice.
you. Visual thinking.
Yes. So the last example, when you require like when you're actually approximating the circulant, you are approximating the circulant in your PGFR.
Yeah, it's really equitable partition kind of thing. So the way I think of those examples is that we have some graph, and then we blow it up into like we blow up some of the nodes into p cycles, basically, and then sort of that's kind of an example that can work. Okay. Maybe it can be generalized to equitable partitions in general. I don't know. That would be a good direction.
It seems like the approximation is something stronger because you are actually having PGST but cycling through your set because you're right?
So no, that's slightly misleading. So the Z matrix is this like directed cycle, but it's only a tool. The way I look at the Z matrix is as a tool to extract the polynomials that I care about. But in the end, this will not be the actual restriction of the, like, it'll not be the unitary block that you see in the UT matrix.
Okay.
So I don't actually think that these will have PGST, and definitely not this directed type of state transfer that you have. And so it's a tool, and it's a little misleading maybe because it feels like it could work, but I don't think it works that way.
Okay. All right. Thank you.